Yo, Mr. Boyle here, and this is section 2.2, which deals with density curves and normal distributions. So a density curve always remains on or above a horizontal axis, and a density curve is something that looks like this, has kind of a little curve over it, and has all the data points in here. Some of you have heard about a bell curve in the past, and it always has a total area of 1 underneath it, meaning that it has every piece of data, all 100% of the data included. When it comes to density curves, we use a symbol that's called mu, which you can't see there, which is mu, and the standard deviation of a density curve is this, I believe it's a gamma, or no, it's a sigma, my bad, on there, which is different than x bar and s of x, which are standard deviations of the actual data. Mean and median for density curves. The mean is the balancing point of the curve, so like where you would put it so that it would balance perfectly on that point. The median divides the area under the curve in half, so half the data is on one side and half is on the other. It's not possible to eyeball the standard deviation on most density curves. If you have a perfectly symmetric density curve, the mean and the median are equal. The mean of a skewed curve is located further or farther toward the long tail than the median is. This goes way back to stuff that we talked about earlier. Remember, skewed data affects the mean and does not affect the median as much. So be really careful about if there's any long tails when it comes to the density curve. Something else that you'll see written is a tall letter N lets you know that it's a normal distribution. And it's always the first number is the mean of the density curve, and then the sigma is the standard deviation of the density curve. Another little thing, when you have normal distributions, which are nice, smooth curves and everything like the bell-shaped curve that people talk about, there's a thing that's called the 68, 95, 99.7 rule, which you'll see coming up in our Check Your Understandings, where it allows you to kind of figure out that one standard deviation out captures 68% of the data, 2 standard deviations out catches 95, and if you go out 3, you capture 99.7% of the data. This is your Z-score formula. Z equals your value minus the mean over the standard deviation, which we worked on in the previous section. Remember, in this situation, since we're doing Z-score, the mean is always at 0, and then the standard deviation goes by 1. There is a table. This is part of something that I've shared with you on Google Classroom, and it's something at the back of our book for those of you that chose to get a book. Something called Table A. We'll go there. It'll help us say, hey, I've got a Z-score of, whatever. What does that mean percentile-wise? Like, what percentile does that put me in, so that I can compare that and use that to make some type of inference down the road. And then that's what they talk about here. Later on, we're going to have to use normality for a given set of data. We have to look at dot plots, stem plots, or histogram in order to do some tests later on in the year. And this 68, 95, 99.7 rule becomes very important, and something we'll talk about, which is a normal probability plot, as another thing that we'll address throughout this school year. Hey, this is Mr. Boyle. I'm out.